Alright, here is the second video for exam 4 that has to do with Pop Quiz 7. So we had a question here. This was a mechanism in which, or a chemical reaction in which we needed to identify that there was a tertiary carbon where the arrow is pointing. And our general model for that is that there's 3 carbons attached to 1 carbon, the central carbon that has the leaving group. So the leaving group here is iodine, and it's going to be replaced, or it's going to be substituted for the O minus CH3 or the methoxide ion. Okay, so here's our general mechanism that in SN1, the rate limiting step, the leaving group leaves, and the result is a carbocation. In step 2, this carbocation reacts with the nucleophile to create the new molecule, which is, so the nucleophile here is OCH3, the leaving group is iodine. So we would pick B. The second question, we're asked about the delta H for this reaction. So we have to do an energy analysis of the bond. So Ci is in the reactants versus CO bond. Reactants have Ci, products have CO. Iodine is really big and oxygen is really small. If we were going to look at the bond lengths, which is going to be proportional to the bond strength, right, using our particulate model, that the Ci bond is expected to be longer than the CO bond. The CO bond is shorter, so we would rank the potential energy this way. So that would give us a delta H less than 0, which would be A. Next, you were asked to construct or select the right rate versus concentration of the nucleophile. So we need to know which mechanism is occurring. Is it SN1 or SN2? Keep in mind that the tertiary carbon is going to be SN1 for our class, primary carbon is going to be SN2, and then the secondary carbon is either going to be SN1 or SN2, and you just need some more information for that. We've already established that this is SN1. So the rate for SN1 is first order overall. It is independent of the nucleophile. 0 order in the nucleophile. We know the nucleophile is OCH3. So since it's 0 order, we would pick B. That's that the rate is independent of the nucleophile, and that is characteristic of an SN1 reaction. Next reaction here, we have what looks like a primary carbon reacting with the nucleophile, so we need to find the mechanism. Is it SN1 or SN2? It's a primary carbon. The carbon that has the leaving group has only one other carbon attached to it. So we know this is going to be a bimolecular slow step. That's what the 2 means in SN2. We could write the rate law as the electrophile times the nucleophile, or the substrate times the nucleophile, however you've heard it, which should be K times our 2 reactants, which means that if we were looking at the rate versus concentration of the nucleophile, which is first order, we would see a nice straight line, which should be A. Next, the energy diagram. So first we need the mechanism, and we've just established as SN2. Single step, right, exothermic reaction. So we've already established it's exothermic. A Ci bond is going to be higher potential energy than a CO bond. So we know it's exothermic, we know it's single step. That evaluation will help us produce a single step reaction that has this form, which would be A. Now we're asked to do the select the energy diagram for the other mechanism. This mechanism has already been established as SN1. This is going to be a 2-step mechanism in which the first step is the rate limiting step. This is the bond breaking of the substrate with the leaving group. We've already established that it's exothermic because it's Ci bond versus CO. Potential energy would rank this way. Since there's 2 steps, there's going to be a carbocation intermediate there. And we expect that overall to be exothermic with the activation energy the highest for the first step. And we would pick C. All right, the next question is about the mechanism in terms of the chirality involved. So let's take a look. So mechanism, so SN1 versus SN2, we're going to have to compare these two. So here we have the case where, remember, this is a product of the tetrahedron. So we have three different groups labeled R1, R2, and R3 in a leaving group. When we do an SN1, we create a carbocation. In SN2, we're going to have just a transition state. Alright, so the carbocation is shown here, and when it's created, it creates a planar structure. So that means the nucleophile can react to the left, or it can react to the right of this carbocation since it's planar. Ultimately, what that does is it produces two different products, the one in which the nucleophile appears on the other side of R1, R2, R3, or it is on the same side as the leaving group originally. So we would get a 50% mixture of these two, since the nucleophile statistically could either react on the left or right of that planar carbocation. SN2 is a different story because the leaving group is still there when the nucleophile reacts. So it cannot appear on the either side. It can only appear on one side. And when it does that, it's going to form a different, the opposite, but 100% pure chiral product. It's not going to be a 50-50 mixture. It will be 100% for SN2. So since we have the mechanism of SN1, we know it's 50%, we expect the answer to be B. Okay, so now we enter the Unit 7 questions that you're responsible for the exam. Here's an example. This is on the worksheet that we will be going over on Friday. So let's take a look. Of course, there's a +1 there. That was fixed. Okay, so let's take a look at the, excuse me, at the chemical reaction. And we're going from an aldehyde to a carboxylic acid. Silver plus is going to silver solid. So we should be able to see that this is going to be a redox. So let's do the analysis. Oxygen and hydrogen do not change signs here. Hydrogen is +1, oxygen's -2, all throughout. What we're going to see is going to be the carbon atoms that are going to be involved in the carbon atom is going to be involved in the reduction or the oxidation, and the silver is going to be involved in the reduction. So we're going to electron count this carbon to find its charge. We give all the electrons in the CO bond to oxygen. We cut the bond to carbon-carbon will be cut in half, and we give all bonding electrons to carbon from the carbon-hydrogen bond. That results in 1 plus 2 to make 3 total electrons around that carbon, giving it a charge of +1. In the products, we have a carboxylic acid here, and so we do the same electron counting. We give all the electrons to the oxygen, all the electrons to oxygen. The carbon will split the two electrons involved in the bond, resulting in only one electron being present. That will then give the charge of that carbon a +3. So we're going from +1 to +3. +1 to +3, and then for silver, what we see, okay, so carbon is oxidized. It's going from +1 to +3. Silver is going from +1 to 0. Silver is reduced. That means that if silver is reduced, it is the oxidizing agent. It is what is oxidizing carbon, and carbon, as it's oxidizing, is the reducing agent. It is what is pairing with silver to be reduced. Keep in mind that the agents are what cause the pair, the other side, to react. And so if carbon is being oxidized, the other substance must be reduced. That's why carbon would be considered a reducing agent. It's the agent that causes the reduction. Silver is reduced, so it's the agent causing the oxidation on carbon. Okay, so with that answer, carbon is the reducing agent, but silver is the oxidizing agent. Carbon doesn't go from -1 to +1. The answer is D. It goes from +1 to +3. Okay, and the last question is, and this is pretty challenging, so let's take a look at it. The idea is that you have what looks like, at least drawn, is that we have all carbons, but we know that's not the case because there's a bunch of protons or hydrogen atoms attached to those carbons. So let's draw the relevant ones. So this molecule here is going to this one. And so we're going to now count the number of electrons. So the carbon, with the arrow pointed to it, will share each of the electron pairs equally with the other carbons. So in this case, it shares 2 of the 4 in the double bond. It will have 2, and each of the single bonds, it'll have 1. When you count that, it's a total of 4. So this one's going to be 0. The carbon on top, though, is going to get 2 from the double bond, but it's going to get both pairs of electrons from hydrogen. When you count that, it's 2 electrons from the double bond, 4 electrons from the hydrogen. It's a total of 6, and it is -2. And this one's 0. So let's take a look at the product. So here we do the same thing. We divide the bonding electrons. So the carbon with the arrow pointing at it is going to have 1 electron from each of those bonds of 3, and it's going to have both of the electrons from the carbon hydrogen. When we count that, that's going to be a total of 5 electrons, which will be -1. This carbon here will get 1 electron from the carbon-carbon bond and all 6 electrons from the 3 hydrogens attached to it for a total of 7 electrons. This carbon here, it will have a -3. So we see that a -2 and a 0 go to a -3 and a -1. In both cases, the carbon is reduced, and so the answer should be B. Okay, so let's keep in mind after looking at this, for SN1, SN2, you're responsible for the mechanism, the rate law, the chirality change in products, and the energy diagram. It's real important to feel comfortable with all 4 of these. Once you identify if it's SN1 versus SN2, you then will be asked combinations of these questions. Unit 7 was about oxidation states, and so you just want to make sure that you can clearly identify all oxidation states of all molecules. You can identify what's being a reducing agent, what's being an oxidizing agent. If you can take this quiz and get 100%, you are well on your way to doing well on exam 4. Good luck, everyone.